Good afternoon. Now we consider conduction mechanism in molecules. The today class will focus on metal molecule, metal systems, and their modeling from electrical point of view. After that, we try to understand how a basic formula, Landauer formula, can be derived by simple physical ideas. After that, we try to apply the Landauer's formula to this kind of system. After that, we try to introduce some correction to take into account the effect of charges in molecular orbitals, the gating effect, and at the end, the strategy to apply Landauer formula when the molecule is described by many molecular levels. So, as you know, our reference system is built up by two metal electrodes, generally gold electrodes, and between them we insert by self-assembly, generally by sulfur and thiol binding, a molecule. So what we are interested in to understand is how current, how electron flux can be described from the left electrode to the right one. So we try to define a model of the system. So we have two tanks of electrons on the left and on the right. So we can imagine that the left tank is the donor or source of the system. In other words, we can imagine that the electron can be originated there. After that, this electron, with tunneling generally, can reach molecule. The molecule is a bridge, and after molecule, electron will be able to reach the second electron tank at the right, that is the acceptor or drain. So in this example, you can recognize what we studied last class. So we have a conjugated molecule, because you see the molecule is done by 4 benzene ring, and so you know that this kind of structure allow a good electrical conductivity, because the p orbital of the benzene ring are overlapping, and so a good molecular orbital for the molecular weight is in the system. So you know also that the molecular and the system can be described by an energetic point of view. On your habit, probably for you it's very simple to describe metals, because metal is described generally by a Fermi-Dirac distribution to understand where the electrons are and which levels are occupied. So in this draw, we can the room temperature in the metal, the Fermi distribution is more and more sharp, because you know that generally states below the Fermi level, μ1, are occupied, and the states up the Fermi level are completely empty. But this is just to understand what Fermi distribution can say us. This is true for the left electrode and for the right electrodes. So molecule is easily described by its molecular level. So we have H level and L level. So you know that the H level is occupied and the L isn't. The problem arises on the interfaces. Interfaces are a problem. We know that the sulfur atom can produce good bond to the metal, but The problem is how the electron can pass through this interface. So we have to understand which is the most effective model for electrons traveling from the metal to the molecule. And the same problem is on the right electrodes. So generally, in a starting model for this kind of system, the electrons can be considered as tunneling electrons. So this interface will be, in other words, will be described by some tunneling parameters. After that, we have the molecular wire. Molecular wire can be short, 2, 3 rings, or can be longer. Probably we have to understand which kind of mechanism of conduction will be more effective in short and long molecules. Probably when the molecule is long enough, the hopping mechanism is more effective. When the molecule is shorter, probably inside the molecule we have a conduction mechanism similar to tunneling. But now we can try to apply some simple ideas to this system. The ideas are based on 2 equations. So here we have the Fermi distribution for the electron 1, for the electrode 1, and for the electron 2, F1, F2. Each of one is characterized by Fermi level, μ1 and μ2, and by the temperature. So this function, as you know, give us the probability that one state is occupied. So when I can write F1 of E, that E means that E is the level, is the probability that the state with that energy is occupied. So this is true on the electrode 1 and on the electrode 2. So this is a number. If you know the temperature and the Fermi level, this function gives you a number, and this number can be used to understand how many electrons are in that state. So this is a simple equation, and we need another one to describe transport starting from the electrons to the molecule. The idea is quite simple again, because we use energetic parameters to describe the interaction between metal and molecular level. This parameter is called gamma in an energy, and we can obtain, starting from gamma, the tau value. Tau is a transit time. In other words, the time required to the electron to travel from the electrons to the molecule. So we can evaluate this time simply doing the ratio between h bar and gamma. So T is a time. We can use that time to evaluate a flux. A flux can be, in this case, described by using 4 different symbols. So you see that on the left you have a flux from the electrode 1 to the molecule, and the symbol is phi x1 to m. And we have also an opposite flux from the molecule to the electrodes. And so the symbol is obviously from molecule to 1. The same thing can be done on the right electrode. So we have 2 possible fluxes from the electrodes 2 to the molecule, phi x to m, and a flux from the molecule to the electrodes. So the molecule is described simply by its molecular level. So we have H level here, H minus 1, minus 2. These levels are completely occupied. And we have L level here, that is most relevant for the conduction, as you know, that is completely empty in this static condition. On this reference scheme, we can define also currents. So we have currents I1. This current describes the total current flowing between the molecule and the electrode 1 at this interface. And I2 is described again as the total current flowing through the interface from molecule to electrode 2. To apply the common current direction, since the electrode 2 is the drain, we prefer to describe a positive current I with this direction. In other words, I1 will be positive for this device, I2 will be negative, because, as I said, we prefer to use traditional current convention. So the current is positive flowing from electrode 2 toward the electrode 1. Okay, so this is the system, and that are the quantity that we want to define. So we try to write simple equation to evaluate the four fluxes. So a flux is a density time dot a velocity. A velocity can be, again, C as 1 over a time. So we can use a very simple expression to evaluate the first flux simply by evaluating the density, the number of electrons at the energy E, and this quantity can be divided by the time required to cross the interface. So the first flux will be simply 2F1 over dot gamma 1 over H bar. In the same way, the 2 is related obviously to the possible spin of the electron in the state. So we are considering just one level. So for that level we have just one possible state. That state can be occupied by 2 electrons at the maximum. And so this is the reason of the 2. 2F1 dot gamma over H. So the first expression, this one, is related to the number of electrons for unit of area for time, a flux, obviously, for the electron traveling from the electron 1 to the molecule. Now we can do the same for the flux of the electron traveling from the molecule to the electrodes. And the expression is similar, is this one, from molecule to electrode 1. So we have N. So N is unknown now, but we can use it to define this possible flux, because we say if we know N, we can evaluate flux, and the flux again is N over time, but time is gamma 1 over H bar. So when the system is at equilibrium, the two fluxes are the same. So we can equal this expression to the second one. So the last expression is just the balance of the two fluxes. The fluxes from the electrode to the metal is balanced exactly by the flux from the molecule to the electrodes. This last expression allows us to write a simple expression for the current I1. So this current can be derived directly from V fluxes. So probably it's better to reconsider the scheme. Current I1, this direction, will be positive when you have a flux of electrons traveling in the opposite direction. So the sign is related to the flux from electrode 1 to the metal. So when you are at the equilibrium, these two fluxes are exactly the same, so the current is 0. But if you have this flux larger than the flux from a molecule to electrode 1, the current will be positive. So what we can write is exactly what I said. So we have, this is the term related to the flux of the electron from the electrode to the molecule, minus gamma 1 over h bar n, that is the flux traveling from the molecule to the electrode. So you know that a current can be directly obtained as a flux dot charge. So Q dot this quantity will be the current E1. It's clear for us that I1 is 0 when the system is at the equilibrium, because I said, and we know, that the two fluxes are exactly the same. We can do the same analysis on the second electrode. So the second electrode has a flux from the electrode to the molecule, this expression. The only change is the 2 instead of 1, but it's exactly the same. And again, we have a flux from the molecule to the electrode 2, that is n, if we know that, dot gamma 2 over h bar. Again, these two fluxes at the equilibrium must be exactly the same, and the current crossing the interface between molecule and electrons on the right is described by this simple expression. Now we are interested, obviously, to understand what can happen when an external voltage is applied. So the idea is to to bias this system by using again an external voltage generator, VA, positive on the right, as usual. And now we try to understand what kind of phenomena are generated by the external bias. You know generally that when you apply a positive voltage to a metal, all the energy band diagram is shifted down by a quantity equal to the energy associated to Q dot VA. So what we can say is the difference between the Fermi level in left electrode and the Fermi level in the second one should be exactly equal to VA as energy, so in electron volt. Now we can do some preliminary analysis. What we have is the LUMO level. LUMO level is this one. So I try to put this level in this position. On the position of molecular level, we have to do some more consideration. But now, as hypothesis, we can understand that this can be a good position, because the electron can flow from the electrode 1 to the L level in the molecule, and from the L level in the molecule can reach the drain, the second electrode on the right. So I try to summarize this condition in this way. The two fluxes red in the scheme are obviously the fluxes that will dominate the current in the whole system. So, sorry. The red fluxes are dominant to understand which is the total amount of current flowing from the electrode 1 to the electrode 2. So, the idea is probably this flux is not zero, because you know that statistically some electron will pass from the molecule to electrode 1 and from the electrode 2 to molecule, but the balance now is not zero, because the balance now is dominated by these two contributes. So what we can do is to write an equation where the sum of the currents, if you remember as we wrote currents, we can say that the device is a node from the electrical point of view, so I1 plus I2 should be equal to 0. From this equation, by using the expression for I1 and I2, we can do a very simple system, and we can obtain an expression for n. N, as I said, is unknown till now, because n is the number of electrons on the molecular orbital. So this expression allows us to evaluate the number of electrons that are in that orbital, in that structure. So now we can substitute n, or in I1 or in I2, it's the same, and we can get this expression. This expression is very common, is used in many fields of nanotechnology, and is called the Landauer formula. This is a formula that can be applied, as we get it, only for one energetic level. Because if you try to analyze this expression, all the quantity are constant, 2, Q, gamma parameters, but also these two numbers are constant, because as you see, the energy E is a well-specified energy, is the molecular level used to evaluate current. So the problem is, if you know exactly the value of the molecular level E, you can estimate current simply by evaluating Fermi distribution F1, F2 for this energy. This is a constant, and we can get the current. Probably is too easy. Probably is not enough to obtain good result. But now we can try to understand just a little better how we can apply this formula. To do that, we can consider these two cases. These two cases can help us to be more confident with that equation. So we can imagine two different conditions. On the left, we have a condition where the molecular level E is there. That means that the function, the Fermi distribution, both on left and on right, are inside the metal, below the Fermi level. What we said at the beginning is that the Fermi function below the Fermi level is approximately 1. So if we try to evaluate F1, F2 for this value of energy, we will obtain 1 on the left for F1 and 1 on the right for F2. But if I try to substitute in Landauer formula 1 and 1, what we discover is the current is 0. So this formula says us that when the molecular level is in a condition like this, current cannot flow, or better, the total current is exactly 0. On the right, we have the opposite condition. Now the molecular level is here, up above the Fermi level of the metal electrodes. And again, you know that the Fermi distribution, just few milli-electron volt above the Fermi level, is 0 at room temperature. So again, F1 of E on the left, F1 of E on the right, will be exactly 0. So 0 minus 0, again, the current should be null. So these are two opposite conditions, but probably are two conditions that we will reach when we try to understand how a molecule will conduct when we try to apply an increase in voltage on the drain with respect to the source. So this is a simple plot by using the Landauer formula. We optimize parameter for T of n, but this is not relevant now. Now we have two values for gamma 1 and gamma 2 equal to 1.6 electron volt. And we fix the molecular level minus 1.47. That means that the level of the molecule is 1.5 electron volt below the Fermi level on the left electrodes. So the idea is quite simple. Now we can try to analyze what I said. So in the system, the electrode 1 is considered as a reference. So the Fermi level here can be used as a reference point. The molecule is simply described by one level, and this level is 1 LUMO level, and this quantity, since this is 0, is minus 0.47 electron volt. That value will be maintained constant. So this is an approximation, but now we are trying to define a simple reference model to evaluate conduction in molecular devices. So what we have is, when the system is at the equilibrium, apply voltage equal to 0, the system probably has this is VA equal to 0. The system is described by this condition. Now, for you, it's evident that the current will be 0, because the function distribution here, as you know, we can try to draw. You know that the function distribution is 0 because one, 0. The same here. So this is Fermi level μ2, and what we have is again a condition like zero is very sharp, 1. So we consider just one molecular level, E, and the position is this one. So it's clear that the value for F1 of E is 1, and also here the value for F2 of the level E is 1. So the Landauer formula tells us that the current is 0. Now we can try to bias the system. As I said, the molecular level is an approximation. The molecular level is kept at this position, and we try to maintain that. And we can imagine which kind of IV curve can be obtained. So when the level of second electrode or the right electrode is pulled down, probably the current will be 0 till the level μ2 will reach the position of the molecular level. So, and the current will be different, will be greater and greater when the molecular level will be there. So we can try to redraw this scheme, just modifying the electrode on the right. So now the voltage should be approximately 1.5 volt, for instance. What we said is the Fermi level of the right electrode will be here, just below μ2. So we can redraw the electrodes, electrode here. So now we have to translate also this one. So I can do that. So now we have to evaluate the value. Will be F2 of the molecular level E. So it's clear that we have a threshold quite when VA approximately 1.415 volts. So the current will be 0 on the left of this threshold, and probably when the right electrode is below the Fermi level, the quantity of current will increase quite. But it's also clear that when you try to increase again voltage, this Fermi function will be quickly 0, and less than 0 is not possible. So what we can understand is that in a very short range of voltages, the current will saturate to a maximum value, like this. So this could be probably what we can obtain by applying in a very simple way the Landauer equation to this system. Now we can check this idea considering what I said. So the molecule, the 2TT, is the blue one, and you see quite well that what we discussed just before. The current is the blue curve. The current is 0, 0, 0, but in the range starting from 1.4 volt, quite quickly it saturates to a maximum value. So Landauer formula can apply very easily, but we are wondering on the quality of this result, and probably you can imagine that the quality of this result is not satisfying, because if you try to compare this IV current curve with the curve that you can get with a simulator, like Virtual Nanolab, VNL simulator, the curves are completely different. So probably your impression is Landauer formula cannot apply to derive, even if we are satisfied by approximated expression, but we cannot use that formula as we do in electronics to derive good model, because it's completely out of our aim. Now we try to understand why Landauer formula in that form doesn't work. And the problem is due to the interaction between molecular level and electrodes. So our idea is, till now, that the molecular level is just one level. But generally, the interaction between molecular level and electrodes produce a broadening of the level itself. In other words, we have this molecular level, and on the interface between metal and molecule, this molecular level is interacts with metal, and we have a broader distribution for that level. So you have a distribution, the function of energy, for a specific molecular level, E. So generally is used in the this kind of correction of Landauer formula, a Lorentzian distribution. So you have a distribution that you can write in this way, is quite similar in shape with a Gaussian one, but the expression is simpler. So you have the energy, E, but this is the level, E again, and we can try to understand if a correction in Landauer formula, taking into account the broadening of molecular level when the metal interact with the molecule, can get us better result. So the idea is quite simple. It's clear that now we have to consider many contributes to the current, each for any energy involved in the transmission of electron. So you see that this one is the original part of Landauer formula. We introduce the density of states derived by broadening of the molecular level, and try to integrate this expression starting on all the possible energies. It's possible also to rewrite this integral by defining the transmission probability as T has 2 pi d of E, and so on. So the expression now is quite simple formally. The current I is equal to 2Q over Q integral of transmission probability multiplied by the difference of the function, Fermi function, in the two electrodes in the range of energy involved by molecular orbital. To understand how we can apply this formula, could be interesting to do this kind of exercise. It's just an exercise, but can be useful for us to understand how we can apply Landauer formula with broadening. So we can imagine that the system is at low temperature. When the temperature is low, what we said on Fermi distribution is completely true. So the F1 and F2 are exactly equal to 1, since on the left electrode F1 is 1, and on the right electrode F2 of E is 0, sorry. So the difference is exactly equal to 1. So the integral now can be evaluated starting from μ2, the Fermi level on the right electrodes, to μ1, that is the Fermi level in the source electrode, on the left electrode. In that interval, at low temperature, the F1 minus F2 is equal to 1. So what in the integral must be evaluated is just the transmission probability between μ2 and μ1. But we know that the difference between the two Fermi levels is exactly equal to the external voltage applied to the system. So what we can do is to consider the average value of the transmission probability at the energy E prime, and we can rewrite in approximated form the integral in this way: 2q square over h VA t evaluated in a medium point as average. So sorry, this term should be omitted, obviously. Now we can do a very simple approximation. We can say we have a system where the transmission probability from the electrodes to the conductive level is 1. If you try to do that, you get a very common expression called G0, that is 2q square over h. That is a quantity that you can measure when you try to characterize, by electric point of view, a single conductive channel in nanosystems. This channel can be simply a wire built up by one atom, each or few atoms, one after one. But now we have to reconsider our system. So the idea that we developed just before to obtain the value of G0 can be applied to the Landauer formula with broadening. So we can say, since the Fermi function also at room temperature are not so different from the Fermi distribution at low temperature, we can apply this approximation. In other words, we can say again that the difference between F1 and F2 for energy between the two values of the Fermi on the left and on the right electrode is equal to 1. And only there, outside this interval, that formula, that difference is equal to 0. Because you know that out of this interval, the two Fermi function will be or both 1 or both 0. So we can transform our integral. So probably it's better to review the starting point. So this is our expression. Now we can substitute for density distribution with broadening is expression, but this term can be approximated to 1. So what we get is simply this one. So here you have the integral now must be evaluated only starting from μ2 to μ1. This is a constant quantity. It can be on the left of the integral. And inside the integral, you have only the state distribution in this form. So what we can do now is to integrate this expression by changing E with eggs as E minus the energy level considered for the molecule. This integral can be solved, and we can obtain a closed form like this. Again, we can try to draw this expression. Again, this expression is enough simple to be used with pencil and paper. So we can try to understand how this expression works. So this is constant. μ1 is constant. This is the energy level of the molecule is constant. Gamma is broadening and should be evaluated or in some way defined. So the voltage, where is the voltage in this expression? So my question is how I can draw current as function of the voltage. The answer is μ2. μ2 is function of the external voltage. When you try to apply a voltage, you can consider a different value for μ2 because the only quantity that is modified by the external bias is the Fermi level in the electrode 2. So this will be function of the applied voltage. And I can draw this expression simply modify the value of μ2 considering the external bias. What we can get now is a IV curve very near, very close to the VNL result. This is a good result. It's not perfect, but now you can recognize the behavior of the curve. It's completely different from the expression and from the curve that we get considering Landauer formula without level broadening. Because if you remember, what we get is a very completely different shape. What is important, now we have not enough time, that this kind of result give us good result also for different molecules, because we can get similar results for longer molecules, for ATT, but also for other different kind of conjugated molecules. So this is a good result, and can allow us to define a simple expression to describe molecular electron devices in terms of current voltage characteristics. The problem is the result is not perfect. We have to fix all these parameters because we have to fix gamma 1, gamma 2 for interfaces. We have to fix to understand the right value for gamma to take into account the broadening. But if we try to do our best, the result is not perfect. And probably for us could be interesting to understand which are the causes of this problem. The problem is charging effect. Charging effect is an important mechanism in nanosystem, in molecular system, but is not so relevant in larger system. In traditional electronic, generally, this kind of effect is not possible to be measured. But in nanosystem, in molecular system, the charging effect can be relevant to the IV characteristics. So now we can try to understand which kind of problem we neglected when we consider the position of the molecular level at a constant level. If you remember, for thiophene, we used minus 1.47 electron volt. So now the system is this one. The idea is to put the molecular level at this point, and after that we try to consider how the electron flow from the electrode 1 to the molecular level, and from molecular level to electrode 2. All it's okay, but now we can recognize an important phenomenon. The phenomenon is when you move an electron from the electrode to the molecule, the quantity of charge in the molecule is changed, but is changed in terms of significant effect, because this electron can modify the energy of the level, the potential energy of the molecule, of the channel, and what we have is this level, when you have one electron traveling along the molecule, this electron contributes to the energy of the molecule itself. In other words, the level will be translate from this position to this one. But it's clear for you that the position of the level is this one, the current is completely different. But if the current is completely different, probably the number of electrons on that level will be different. So what we have to do is to consider a closed system where we have to consider current. From the current we can understand and we can evaluate the average number of electrons on the molecule. That number modify the energy of the molecule, and so on. So the problem that we have with molecular system like that is to consider also the effect of the charges traveling on the system. How we can do that? It's not easy, and we cannot do that with simple formula. So probably for a simple description of molecular electron devices, we cannot do. But the idea is this one. We have to satisfy this kind of equation. So this is the equation that we derived for the number of electrons on the molecular level. This number depends only on the value of molecular level. In this case, we call this EI. This number, N, can be considered to evaluate the energy of the due to the additive or subtractive number of electrons on the molecular level. So we have to evaluate the difference between N and the value at the equilibrium, and starting from that, we can evaluate the value of potential energy for the molecular level. So in this way, we can update the value of the EI in EI plus 1, and so on. So the system must consider in a closed form this equation. Generally, this kind of algorithm of procedure is done by simulator, but obviously for us it's very difficult to implement it by a simple closed form model. So what I can say, if we need to manage a simple equation to describe molecular devices, is to use a approximated value for the molecular level, and we have to accept some errors deriving from this approximation. But it's not possible to implement closed form equation taking into account charging effect. Charging effect is important because in the next classes you will see how molecular system can be described also in terms of Coulomb blockade, because this is a typical effect that modify the IV curves in nanosystem. The question general is, but on a molecular device like what that we studied now, Coulomb blockade can be observed. The answer is depend on the interfaces. So if you have good interfaces in terms of charge transfer, generally it's very difficult to measure Coulomb blockade. Coulomb blockade can be very easily observed only when the interface have a bad transport. So if the tunneling between metal and molecule is not so good, in that cases you can observe Coulomb blockade. In other words, if you are building, if you are implementing a molecular device to transport electrons in an efficient way, generally that kind of device is not affected by Coulomb blockade. If you want Coulomb blockade, you have to make the interface less efficient. So the tunneling should be less efficient between electrodes and molecules. In that case, you can observe very well Coulomb blockade. Now, we can consider also gating. We know that molecular wires can also be used to to implement molecular field effect transistor. It's also clear that you need a third electrodes to control current. The idea generally is what you see on this slide. So this is our bridge, molecular bridge, the two electrodes, source, drain. Here you have a very thin layer of insulating material, dielectric. Below you can put another electrode. So you can apply an external voltage to modify or to apply an electric field, a vertical electric field, to the molecule. So what can be interesting is which is the effect of this external field. We can consider a condition not completely different from that we consider for charging effect. Because on the left we have a system, this one, where the molecule level, L level, is here, could be. It's clear that when you have a gate voltage equal to 0, the position is this one. It's clear that the current in this system will be 0. Will be 0 because the function, the Fermi function, will be 0 both on the left and the right. The difference is 0, but it's clear also from a physical point of view because electron here there are not electrons, so the flux is impossible. Now we try to apply a potential here, for instance, a potential of 1 volt, and you know that this potential push down all the levels of the molecule below. So what we can observe is the external gate voltage will push all the levels of the molecule level below. But if the voltage is large enough to put the L level in this position, it's clear for all of us that the current now can flow, and you have a large amount of current flowing from the electrode 1 to the electrode 2. So the effect is to control the current from 1 to 2 simply by moving, by translating the energy levels of the molecule between the electrodes. This is an idea but it's not a good idea, because in the next classes you will consider some result, experimental result obtained in this direction, and what is clear is that this is a good idea to measure and to understand this kind of phenomena, but it's not a good idea to design and to realize molecular devices, because in this condition, if you imagine how you can realize this system, probably all the advantages of molecular technology are lost, because again you have to realize a well-defined dielectric, very thin, because the maximum thickness of this dielectric probably should be less than 1 nanometer. If the dielectric is thicker, the quantity, the electric field is not enough to modify the molecular level. So in this way, all the advantages of molecular electronics, self-assembly and so on, are lost. So it's not a good idea, in my opinion, to define for molecular device structure like this. But the idea could be interesting, because probably we can implement other structure where the effect of the electric field can be measured only as a measure of the current between two metal electrodes on a molecular wire. So the last thing is multi-level system. It's clear that molecules generally are not defined only by one L level. We know that generally molecule can be described by more than one. So here you see that many LUMO level are in the molecule. So you see that here you have the first one, another one, another one. What is this curve? This curve is the transmission spectrum for a molecule interface, metal molecule interface. And so you see that the broadening appears on different level. So this is a conductive level. You have another one, increasing the energy. But each level will be larger than a simple level like we have in insulated molecules, and are composed in this way. So the Landauer formula can be extended also to this case, because in general it's quite easy to understand if you have more than one molecular level, you have to consider the sum of the contribution of level 1, level 2, and so on. So more level you have, more current you can transport from source to drain. Depend on the position of the level with respect to the Fermi level in the metal electrode. This is clear, because the exercise that we did just before can be applied to a system where the level are more than one. But the idea is exactly the same. So the integral must consider more than one level, and so the current probably depend on the position of the level with respect to the Fermi level in two metal electrodes. But the Landauer formula can be obviously extended, because we can consider a more complex transmission spectrum in the formula that we derived just a few slides before. In other words, we can use this formula. In this formula, we can substitute this transmission with a transmission that contains more than one level, and the integral can evaluate the total current, obviously knowing how the spectrum is Okay. In order to summarize what we try to understand today, we can consider this simple scheme. So, when we want to design, to understand how a molecular electron device works, obviously the reference equation is Landauer formula, because it's a good compromise between simplicity and reliability in terms of result. Landauer formula must be used if you know molecular levels. Molecular levels depend on the molecule that you are using between electrodes. So, from the analysis that we are able to do, we can define the energy levels, the energy band diagram, like as in semiconductor, if you know HOMO, LUMO, LUMO plus 1, plus 2, and so on. Obviously, these levels are affected by different phenomena that doesn't depend directly by the molecule, because you know that the molecule charges must be evaluated as function of the applied voltages. So this level should be corrected by effect of charges on molecule. And obviously also the gating has a similar effect. So charges and gating can be, in other words, described in very similar way simply by modifying the position of conductive channel in the molecule. Landauer formula requires also that you have the binding with electrodes, and the binding with electrode is described by gamma 1, gamma 2 parameter and by level broadening. So all these parameters can be approximated and can be used to evaluate the current voltage curves with a good approximation. Obviously, the most critical part should be this one. For an approximation of this equation, for us it's very difficult to derive a closed form for the effect of charges on molecule. Generally, what we can do is to put the energy levels, the position of the energy levels, to an average position to get a good result, but cannot be exactly defined only with an approximated system. Obviously, if you need more accurate result, a simulator must be used. Okay, thank you. Any question?